This question is a tough one, I think. The only advantage, really, or plus to the question is that, okay, a couple of the questions are show that questions, and so if you don't make progress with them, you can still make progress later on. I'd say especially Part E because of how it helps you in C, but there's plenty of places to lose marks, changes of sign and just things to miss. Let's get into it. So we have a circular tower here which stands in a large horizontal field of grass. A goat is attached to one end of the string, and the other end is attached to point O. So got a point here. Then the string has length pi. We can ignore the size of the goats, and the curve C, this interesting curve that's going on, represents the edge of the region that the goats can reach. First of all, we're asked to write down the equation of C for y is less than 0. So that's just going to be here. And there's no impediment. The tower is not impeding the goats here. So it's just going to be kind of the maximum area that you can get. It's going to be a circle. And it's centered at the origin. So it's going to be x squared plus y squared. Now we just need to think about the radius. But remember, it said the string has length pi. So that means this distance is going to be pi. And the radius is therefore going to be pi. So answer to the first part is going to be x squared plus y squared is equal to pi squared. Now, don't let that question give you a false sense of security. We're into the main bit now. So when the goat is at point G, X, Y, here, for example, with X greater than 0 and Y greater than 0 as shown, the string lies along OAG, where OA is an arc and AG is a tangent. So we can see this arc coming round and then it's a tangent because it has to get around the tower. It can't go straight to from O to G using a straight line. We're asked with the aid of a suitable diagram to show that x and y can be represented parametrically. Okay, let's give it a go. So I'm only going to look at the positive x and positive y axis. Remember, I've got this circle that is occurring a little bit like that, and it continues round, not a bad circle. And then G is the path that the goat can take. And it looks a little bit like that. It's not bad. I'm not doing it exactly to scale. We've got the origin. We've got the point O. And the rope is going along here. And then we've got this tangent that goes to G. We're also told about point T. And then there's a line that goes. Just going to put that A in again. So there's a line that goes to this point, and this is going to be A. And this is theta. So how to try and describe this coordinate using theta? Well, remember, we're at the origin and then we're going some amount along. Now I can create a right angled triangle here. And this length is 1. And that will allow me to work out this distance here. Because if I draw it over here, then actually this, as you move this in towards the angle, you get cos theta. And the opposite is then sine theta. You could also label it question mark, and if you didn't spot to do that, and you could say that sine theta is going to be question mark over 1, and then you'd see that question mark is simply sine theta. So that is how far we're moving in the x direction to get from O to A. And I said one other thing. I said that this distance is going to be cos theta. Therefore, this, well, remember from T to O was a distance of 1. So that means this distance from O up to A in the y direction is going to be 1 minus cos theta. Brilliant. Now we've just got to work out how far we move in the x direction from A and in the y direction as well. Okay, for that I'm going to need to think about the arc length. Okay, I've kind of drawn the arc along. I've run out of space. So the arc length, because we're working for the angle in radians, is going to be r theta, which in this case is simply going to be theta since r is equal to 1. And that is really crucial because it allows us to work out this distance, because the whole thing, remember, is pi. And therefore, this distance is going to be pi minus theta. Now, I've got the radius meeting point A and also meeting a tangent. We'll have 90 degrees here. This little angle, I'm not going to label it, but it would be pi over 2 minus theta. And then I have another pi over 2. And what we'll get is that this angle is also theta. And we can use a similar argument to over here to get the lengths. And running short of space, but this one is going to be pi minus theta times by sine theta. Okay, because it's opposite the angle. I've just used trigonometry. And then this distance I'm pointing to, can just about fit it all in, is going to be pi minus theta times cos theta. That's a pretty decent argument, I think. I've said a lot in spoken words, but I think anyone looking at this should be able to see what I've done, I hope. And therefore, for g, x, y, x is going to equal sine theta to get from O to A. And then we're going to add pi minus theta cos theta. By the way, that is here. And then y is going to be 1 minus cos theta to get from O to A, this distance. And then I'm going to be adding pi minus theta sine theta. So through this geometrical argument, we've managed to write down x and y parametrically for x greater than 0 and y greater than 0. Next up, part C, which I think is the most challenging part of the question. So we're asked essentially to integrate parametrically to show that the area between C, the positive x-axis, and the positive y-axis can be written as shown. What we're asking for is this area here in green. Okay. So I'll call this R, and it's going to be, first of all, the integral from 0 to pi of y with respect to x. Because remember, like that, the point at which, let me just show you. Yeah, here we go, 0 to pi. But of course, we want to change that to a parametric integration. So it's going to become y dx by d theta using chain rule. Now I need to think about what values of theta I get when x is 0 and when x is pi. Okay, well, when I'm going to return to the original diagram, when x is equal to pi, we are going straight from O along the horizontal axis. And that will mean that theta will actually be, well, it will just be it'll be going like straight down from here to here. So there won't be any angle. So essentially when x is pi, theta is going to be 0. Let me just say that again, because I just want to kind of map out what would be going on. We've just got this point here. So if we're at the, well, not at the point T, but the angle that we'd have to make to get to this here would just be 0, and then we'd be going straight along. So when x is pi, theta is 0. And then we need to look at when x is 0. And in that case, when x is 0, we're talking about this being the what the string would look like. And theta, in fact, would be going all the way around. What we get is that theta is in fact pi. I think this is quite challenging personally. Easy to miss that, or like not realize that those are the limits that you have to change to. One alternative, of course, is to take these equations that we've shown. Sorry, I didn't actually manage to take all of it. Let's try again. Okay, and try to substitute x equals 0 in. So this is now purely from an algebraic approach rather than looking at the geometrical picture. So I'd say this is the way you want to go if you can, trying to visualize it. But if you don't see that, then this is just an alternative. So we've got the when x is equal to 0, we're going to get that 0 is equal to this. Now this is not actually an equation that you can really solve because you've got a trig function, but you've also got a theta in there. So you'd have to just look at this and think, well, how can I get x equaling 0? And it's going to have to be when theta is equal to pi to be able to like eliminate this term. So it's kind of just almost like a trial and error, or sort of just observing the solution. And when x is equal to pi, we'll get that pi is equal to sine theta plus pi minus theta cos theta. And to get the pi, right, we need it here really, so we're going to need theta to be 0. And we can see that that then works. So I kind of try a value and I see that it works because sine of 0 is 0, cos of 0 is 1. I'm minusing 0 here, I'm going to get pi. In any case, we've got this here, so right, we're on our way. Now we just need to do this integration. So I've got my limits, I've got my y, I just need to work out dx by d theta. And that's going to be cos theta plus, and then I'm going to have to use the product rule on this. So I'll call this u and this v. So if I differentiate u with respect to theta, I'm going to get -1. And then I times by v, I'm going to get cos theta. And I get u times cos differentiated, which is going to be minus sine. Fortunately, these cancel, and we're just left with minus pi minus theta sine theta. Now I'm going to leave it like this. You could write it as theta minus pi, but I'm going to be consistent with all the rest and keep it as pi minus theta. And there's a reason for that, which we'll see in a minute. All right, therefore, r is equal to the integral from 0 to pi of y, which is 1 minus cos theta plus pi minus theta sine theta multiplied by minus pi minus theta sine theta, and then we just need a d theta in there. Frustratingly, I didn't leave enough space. I'm just going to write it out again. Okay, and remember, we're not trying to do this whole integral. We're trying to show that it can be rewritten in terms of u like this. Note there's a u in there. So we've got theta. It's changing to u. We're going to have to do a substitution. Now, sorry if I just slide a little bit there, but yeah, there's quite a lot to do in this question, isn't there? And we're not there yet. Um, we've, I suppose, in effect, like it hasn't been too bad. It's just getting the limit and now doing the substitution. Of course, we could expand it out, but I'm not going to expand it out quite at the moment. I'm just going to like look at what is going on. I see that I'm going to get a cos theta sine theta term, but here I'm timesing by u, and here I'm timesing by pi minus theta. What else have I got? I've got a sine squared term, and then I've got a u squared, and again I've got a pi minus theta and a pi minus theta. So what I'm going to do is my substitution is going to be to let u equal pi minus theta. Now, it might be quite easy in this question instead to do a substitution of theta minus pi. That is an option. That can still get you there, but you will have to then do a later substitution to make it like v equals minus u or something, because otherwise it won't quite come out. So really want to go with this one, but you might have changed this to theta minus pi and done that substitution instead. You can get there, it's just going to take more steps. So when theta is equal to 0, u is equal to pi, and when theta is equal to pi, u is going to equal 0. That's good because that's going to allow us to swap our limits around. We then just have to think about a couple. Okay, right, I'll write the next bit down. So it's going to be r. Oh, I'm going to get that du by d theta is going to equal minus 1. So r is now going to be the integral from 0 to pi of 1 minus cos. Of course, if I let u equal pi minus theta, then theta is going to become pi minus u. So I'm going to get pi minus u here. But here it's going to be a bit simplified because I'm going to get a u and then sine pi minus u. Okay, that's all in a big bracket. Then this is still in the integral, then I'm going to be timesing by minus u sine pi minus u. And then it's going to be times minus 1 du, because I have to times by du by d theta. I'm going to cancel that minus 1 out with this minus here. We're not far away. You can see in the answer though, we've got things in terms of sine u and cos u. So we need to think about what these functions are. You might know the result, or you might draw the graph and think about the transformation, although it's an awkward one because you've got a translation and a reflection essentially. So I think it's a bit safer to use addition formulae. You're going to get cos pi cos u, and then it's going to be plus sine pi sine u. But the sine pi disappears. Actually, cos pi is minus 1, so I get minus cos u. Okay, like I said, you might have figured that out from transformations. and sine pi minus u. Actually, another way you could have done this, like a bit easier with transformations, is to realize that cos is an even function, so this will equal cos of u minus pi, which, if this is cos, this is going to be a translation by pi in the x direction, and if you do that, so that should be coming back down, then it will in fact look just like the opposite. Okay, it'll be this reflection. So yeah, you can get there that way as well. Sine pi minus u is going to be sine pi cos u minus sine u cos pi. Okay, again, this cancels. Cos pi is minus 1, and I actually get sine of u. And in this situation, I could have used the fact that sine is an odd function and written it as sine u minus pi, but it's actually minus sine u minus pi. And then thought about, right, well, I've got sine. I'm going to do a transformation where I move it to the by pi in the x direction, which would mean that it becomes like this. And then I'm going to make it negative, which will take it back onto itself. So you can, yeah, you can get there that way. But these are two crucial results we'll now need. Okay. Therefore, r is going to be the integral from 0 to pi of 1. Now remember, this is minus cos u, so it's going to become plus cos u plus u sine u. And then I'm going to be multiplying by u sine u and integrating with respect to u. Whew. We're nearly there. Let's expand the brackets, first of all, within the same integral. In fact, I might just write it here to get a little bit more space. So it's going to be u sine u plus u sine u cos u plus u squared sine squared u du. And finally, I can just split it into 3 integrals. So we'll have u sine u integrated. Then I'll put the sine squared one next, as is in the answer. And then finally, u sine u cos u. Okay, well done if you got that. Challenging, I think, but we're there. So we've completed A, B, and C. A was a long time ago now. B was that parametric part, and C was this integration, parametric integration, to leave us 3 other integrals that we're yet to do. Part D is asking us to focus on the middle integral and show that it can be rewritten as this. And then finally, we're going to find the area of the grass reached by the goat. So we'll come back to that in a minute. Right, D. Now, we've got an integral and we're still going to have another integral left. We've got a product of functions. This is looking a lot like, and we're going to need integration by parts. Now remember, when you do integration by parts, you typically want your u to be this thing that's going to get simpler. So this is going to have to be u, okay? Because if I let this be v dash, it's going to become a third v cubed. A third u cubed. Yeah, that's going to be heading in the wrong direction. So although we might not want to integrate sine squared u, we're going to have to. U dash is therefore going to be 2u Right, we've got a little bit of work to do with b dash, because at the moment it's sine squared. But there's a standard method for how to deal with this, and that is to use double angle formulae. Cos 2a is actually going to be cos squared a minus sine squared a, and we can substitute in for cos squared 1 minus sine squared, and so we get 1 minus 2 sine squared. And therefore, sine squared, you can rearrange it, and it's going to be a half minus a half cos 2a. So that means if we integrate it, then v is going to be a half u minus a quarter sine 2u. I've just kind of taken this and replaced the a by u and then integrated it. Okay, that's what we're going to get. So that means that this here is going to equal, it's going to be uv. So u squared times a half u minus a quarter sine 2u, evaluated between 0 and pi. Then I'm going to be minusing the integral from 0 to pi of u dash, which is 2u, then times in by v, a half u minus a quarter sine 2u. This is going to equal, I'm going to put in pi, so I'm going to get pi cubed over 2 when I substitute in here. Now when I substitute in pi for the sine 2u term, I'm going to get sine of 2 pi, and that's just 0. And then when I substitute in for 0, I'm also going to get 0. So actually I've done this integral here. I've just got pi cubed over 2. Then I'm going to get the integral of, I'm going to separate this into two integrals. So this 2 is going to cancel with the half and partially with that 4. So I'm going to be minusing u squared, which I'm integrating with respect to u, and then actually adding the integral from 0 to pi of a half sine 2u. This is going to be pi cubed over 2 minus, it will be a third u cubed, evaluated between 0 and pi. And now remember, we're not actually trying to do the whole integral. We've still got an integral at the end. And sine 2u, in fact, can be written as 2 sine u cos u. So this will simplify to precisely what we needed. In the equation, I've just also forgotten to put the half in there. Sorry, that's better. Okay, because it would have been easy to do that integral otherwise, but I needed that there. Apologies, it's there now. So it's going to be a half u times 2 sine u cos u. So that would take me to u sine u cos u. When I substitute in, I'm just going to get pi cubed over 3 plus this same integral. I'm not going to write it out. And this is 3 pi cubed over 6 minus 2 pi cubed over 6. So I'm going to get pi cubed over 6. Okay, we've done this. We've shown that this integral here is equal to this integral here. We are left with the small matter of calculating the area of the grass that can be reached by the goat. So it's going to be this in red, this in blue, and this in green. Well, if we just look at the red and the blue area, the top area, then it's going to equal 2r, because that r, as remember, was the area of just the between the curve and the axes for positive x and positive y, but I'm going to get exactly the same for negative x and positive y. But then I'm going to need to subtract the area of this circle inside the tower takes up. So the radius was 1. It's going to be pi times 1 squared. We're just going to need to minus pi for that. And then add on this green area, which is going to be a half of a semicircle. So it's a half pi times the radius squared. But the radius here is pi. So it's going to be this. And I'll just write that out again. So it's going to be 2r plus a half pi cubed minus pi. And this is what we need to focus on, finding r. Now, from previous, we had that r was equal to this, and we had one of the integrals. So therefore, r is going to be the integral from 0 to pi of u sine u with respect to u. And then I'm going to add on, right, we've calculated this one, so it's going to be pi cubed over 6 plus the integral pi u sine u cos u du. But then I'm just adding on another one. So in fact, I've just got two lots of that integral. I'm going to focus on the first integral. I can use integration by parts on this, and I know that I've got u in the integral, but I'm just going to kind of treat it as if it was an x. So I'm going to call this one u and this one v dash, because we're going to do integration by parts and try and make it simpler. Then u dash will be 1, and v will equal minus cos u. So we'll get uv, which is actually minus u cos u, evaluated between 0 and pi. And then it's going to be minus the integral of u dash v, which is minus cos u, between 0 and pi. And the minus will cancel with the minus, and this will become a plus. We need to do this integral. You can actually do it really quickly if you draw a little sketch of cos and realize that between 0 and pi, you'll get exactly the same positive integral here as negative here. This will equal 0. If you don't spot that, of course, you can integrate it to sine u, substitute in 0 and pi, and yeah, you'll get 0 that way. So we're left with substituting in pi minus pi cos of pi minus 0. Cos of pi is minus 1, so we get pi as our answer. Okay, this is pi. Okay, now I've just got this one to deal with. And it was two lots of the integral u sine u cos u between 0 and pi. Now, before we put it in this form, I think it was in part C, actually, there was a better form for it, because we can write it as u sine 2u, which massively simplifies it, because I don't have three things multiplied together, just two. Now, again, I'm going to do integration by parts. That one is my u, that's my v dash. So u prime is 1, and v is going to be minus a half cos 2u. So I'm going to get minus a half u cos 2u evaluated between 0 and pi, and then I'm minusing the integral 0 to pi of minus a half cos 2u. Because it's a minus again, that will become a plus. For the same reasons as before, now we've got cos 2u. All that's going to do is stretch it, and then this negative bit will cancel with this negative bit, and that negative bit will cancel with this positive bit. Hope I explained that all right. So again, that is going to be 0. Again, if you don't spot that, just integrate it. You'll get a sine 2u. When you substitute in pi and 0, it will be 0. So this will be minus a half pi times cos of 2 pi, which is just 1. And then when I put in 0, I'll get 0. So we've dealt with that. Hence, the area will equal, now we can put it together. We've got 2 lots of r, and we've just figured out r. So it's going to be 2 lots of pi plus pi cubed over 6 and then we are we're adding this integral, but it was equal to minus a half pi, so minus pi over 2. Okay, that's the 2r part. Then we've got plus a half pi cubed, and then we're minusing pi. So that will be 2 pi plus pi cubed over 3 minus pi plus pi cubed over 2 minus pi. The 2 pi and the minus pi will cancel. So we're left with, we can put it over a common denominator. It's going to be 2 pi cubed over 6 plus 3 pi cubed over 6. And we're there. The answer is 5 pi cubed over 6. That is going to be the area that the goat can graze. Okay, that was a long, long solution. I gotta say, probably the longest I've ever written on these AEA papers. Well done on your efforts.